Tornadoes are very unfortunate storms we have. Thousands have lost their lives to be storms. Tornadoes form when warm, moist air collides with cold, dry air, creating atmospheric instability. This temperature clash fuels severe thunderstorms, most commonly supercells. Inside the storm, wind shear, winds blowing at different speeds and directions at varying altitudes, creates a horizontal spinning tube of air. Strong updrafts within the thunderstorm tilt this horizontal rotation into a vertical column. As the column narrows and spins faster, it stretches downward, becoming a tornado when it touches the ground. The two countries that have had some of the worst tornadoes in all of human history are the United States and Bangladesh. Determining what the worst tornado in human history is dependent on how you view the size of it, its damage or its casualty. If we look at casualties, the 1989 Dolat Persitoria tornado was the worst, killing 1,300 people. But today, we're gonna be looking at the widest tornado ever, that happened in 2013. May 31, 2013, the most monstrous largest tornado that has ever stepped foot on this planet. At its peak, this massive storm reached an unprecedented width of 2.6 miles (4.2 kilometers). It was large enough to fit both the two smallest countries in the world inside of it, the Vatican City and Monaco. So what happened on that fate day, only 12 years ago? For meteorologists, storm chasers, and weather enthusiasts across the United States, it seemed like another dangerous day on the Great Plains. A powerful storm system was developing over central Oklahoma. The ingredients for severe weather were all in place: warm, humid air streaming north from the Gulf of Mexico, powerful winds higher in the atmosphere, and enough instability to fuel violent thunderstorms. The ingredients for severe weather were all in place: warm, humid air streaming north from the Gulf of Mexico, powerful winds higher in the atmosphere, and enough instability to fuel violent thunderstorms. By late afternoon, storm chasers from across the country had converged on the Oklahoma City area. Many of them believed they were about to witness another significant tornado. What they didn't know was that they were about to encounter one of the strangest and most dangerous tornadoes ever recorded. What began as an ordinary tornado warning would evolve into a storm unlike anything scientists had ever seen. A tornado so large that it would become the widest ever measured. A tornado with wind speeds approaching those found in the most violent storms in history. A tornado that would suddenly change direction, expand without warning, and trap experienced storm chasers in its path. And a tornado that would claim the lives of some of the most respected researchers in the field of severe weather. This was the El Reno tornado. Just 11 days before the El Reno tornado, another tornado had captured national attention. On May 20th, a massive EF5 tornado struck the city of Moore, south of Oklahoma City. With winds estimated at over 200 miles per hour, the tornado devastated neighborhoods, destroyed schools, and killed 24 people. Images of the destruction were broadcast around the world. For many residents of central Oklahoma, the disaster was still fresh in their minds. Meteorologists knew that the pattern responsible for the Moore tornado was still influencing the region. At approximately 6:03 p.m., a tornado touched down near the town of El Reno. At first, it didn't appear extraordinary. In fact, compared to some of Oklahoma's most famous tornadoes, it looked relatively unimpressive. The funnel was narrow. Its condensation funnel wasn't particularly dramatic. And from a distance, it seemed like just another tornado on the Oklahoma plains. Many storm chasers had seen storms that looked far more intimidating. But appearances can be deceiving, which was right in this case. Across western Oklahoma, hundreds of storm chasers were moving into position. Some hoped to capture dramatic footage. Others were gathering scientific data. Among them was one of the most respected tornado researchers in the world, Tim Samaras. Unlike many television personalities associated with storm chasing, Samaras was known primarily as a scientist. For years, he had worked to better understand tornadoes by placing specialized instruments directly in their paths. His team, known as TwistX, short for Tactical Weather Instrumented Sampling in Tornadoes Experiment, had contributed valuable data to tornado research. Tim, along with his son Paul Samaras and fellow researcher Carl Young, was monitoring the developing storm. They were not alone. Dozens of experienced chasers were converging on the same area. Most believed they understood what the tornado was doing. But the tornado was about to do something few of them expected. Between roughly 6:10 and 6:20 p.m., the storm underwent a dramatic transformation. The tornado continued expanding. Multiple smaller vortices began rotating within the larger circulation. The structure became increasingly chaotic. From the air, or from radar, the storm was beginning to resemble a massive rotating complex rather than a single, easily identifiable funnel. Yet many people on the ground couldn't fully appreciate what was happening. Heavy rain concealed much of the tornado. Distances were difficult to judge. And the storm's true size was becoming almost impossible to comprehend. What appeared to be a tornado a few hundred yards wide was evolving into something measured in miles. The circulation was growing rapidly. Much of that growth was hidden by rain. Many people could only see a small portion of the storm. The visible funnel did not reveal the tornado's true size. Mobile Doppler radar teams were collecting data near the storm. What they found shocked meteorologists. The radar detected winds approaching 300 miles per hour. Those are among the highest tornado wind speeds ever measured. There were few buildings available to demonstrate the tornado's full destructive potential. As a result, the storm would later receive an EF3 rating. The El Reno tornado was now at its most dangerous stage. Hundreds of storm chasers were scattered across the roads surrounding the storm. Many believed they understood where the tornado was located. What they didn't realize was that the tornado was continuing to evolve. Heavy rain wrapped around much of the circulation. Visibility became increasingly poor. The storm's true size was difficult to judge. From some angles, the tornado appeared much smaller than it actually was. Roads that were normally quiet began filling with vehicles. Researchers, photographers, television crews, and independent chasers were all attempting to track the same storm. The increasing traffic created a new problem. Escape routes became crowded. Turning around quickly was no longer easy. At the same time, the tornado continued expanding. Meteorologists monitoring radar noticed unusual changes in its movement. The tornado was not behaving like a typical plains tornado. Its circulation became increasingly complex. Multiple vortices rotated around the larger parent circulation. Some of these vortices contained extremely violent winds. The danger zone was growing larger by the minute. Then the storm began changing. This unexpected movement caught many people off guard. Positions that had seemed safe only moments earlier suddenly became hazardous. Several storm chasers realized they were much closer to the tornado than they had believed. Vehicles began accelerating away from the storm. Some drivers searched desperately open roads. Others attempted to reposition before the circulation reached them. For many people, the chase had stopped being about observation. It had become a race to stay ahead of the tornado. And for a few individuals, there would not be enough time. Tim, Paul, and fellow researcher Carl were carefully monitoring the storms. But the tornado was still changing. Radar data suggested the circulation was shifting. The storm was not following a simple, predictable path. Heavy rain continued to obscure the structure of the tornado. From the ground, it was difficult to see what was happening inside the circulation. As Therm moved, Twistex attempted to maintain a safe distance. But the tornado was becoming larger and less predictable. Traffic on rural roads was increasing. Some roads were becoming congested. Escape routes were narrowing. Then the tornado made another shift. The storm was no longer confined to a clearly defined path. It was a broad, evolving circulation moving across open land and road networks. At some point during this phase, Twistex became critically close to the circulation. The exact details were difficult to reconstruct later due to visibility and radar limitations. But what is known is that conditions deteriorated rapidly. The tornado overtook portions of the area where multiple chaser teams were located. Vehicles were affected almost instantly. Some were impacted directly. Others were caught in outer circulations and extreme winds. Among those in the path were Tim Samaras, Paul Samaras, and Carl Young. All three were killed when their vehicle was struck by the tornado. The loss shocked the meteorological and storm chasing community. Tim Samaras had spent decades improving tornado safety and understanding. His work he contributed significantly to modern storm research. The fact that he was killed by the very phenomenon he studied deeply affected many researchers. In the aftermath, questions were raised about tornado behavior that day. Tim Samaras had spent decades improving tornado safety and understanding. His work he contributed significantly to modern storm research. The fact that he was killed by the very phenomenon he studied deeply affected many researchers. In the aftermath, questions were raised about tornado behavior that day. The tornado continued moving after the most dangerous encounters on the ground. But the worst of the human impact had already occurred. When the storm finally weakened and dissipated, central Oklahoma was left to assess what had happened. However, the death count was extremely low, with only 8 people being killed. The El Reno tornado had become one of the most studied tornadoes in modern history, not because of the damage it caused, but because of how it behaved. In the days that followed, meteorologists began piecing together the full structure of the storm. Radar data, field surveys, and video footage were analyzed in detail. What emerged was a picture of a tornado far more complex than initially understood. Approximately 2.6 miles across, it remained the widest tornado ever recorded. Luckily, it only hit areas that were unpopulated areas, but it still had a huge impact in the region.